And we will now finish this lecture with an application. And here I would like to present you how the structure of beta-carotene was elucidated already several years ago. And it is a nice application, as at that time the oxidation of the carbon-carbon double bond was very helpful for elucidating the structure of beta-carotene. What was known about this compound? At the beginning, it was only known that there is a compound which has a strong orange absorption and which can be extracted from different natural products, for example, from carrots. But the structure of this compound was totally unknown. And for elucidating this structure, the chemists used several different chemical techniques in order to analyze the chemical properties of this unknown molecule. And amongst others, several oxidation techniques such as the reaction with potassium permanganate or also ozone were applied. And now I would like to briefly guide you through the most relevant steps on how to elucidate the structure. So at the beginning, they just knew that there is a molecule which consists only of carbon and hydrogen atoms. So this was known. And then they already knew the molecular formula, which was C40H56. And as you know, if we have an alkane, which is fully saturated, we always have a molecular formula with Cn and then H2n plus 2. So if we would have a fully saturated alkane, we would expect to have a molecular formula of C40H82. However, there were only 56 hydrogen atoms and not 82. Hence, there was a difference of 26 hydrogen atoms, which could be explained with the presence of 13 carbon-carbon double bonds. However, then the chemists also knew that there are only 11 pi bonds. So how could you then explain this difference in hydrogen atoms? The solution is that there must be 2 carbon-carbon rings. Furthermore, it was known that this molecule shows no optical activity. Hence, this molecule can not contain any chiral carbon atoms. This was also an important knowledge. And yeah, that was the starting point. And then mainly Paul Carra started with some oxidation experiments. And he wanted to elucidate the structure of this unknown molecule based on the results of his oxidation reactions. So in other words, he wanted to conclude based on the oxidation products which starting material he had. And he started with the reaction with potassium permanganate. And he found this beta-enone molecule and 4 equivalents of acetic acid. Afterwards, he used a stronger oxidation agent, and then he found 6 equivalents of acetic acid. And based on these results, he concluded that there must be 6 methyl groups directly attached to a carbon-carbon double bond. Finally, he did some further experiments, and the main result was that there is only one isomer. Hence, he concluded that the unknown molecule must have a symmetry. And based on all these experiments, they figured out that this unknown molecule looks like this. And what you can see is that Paul Carra was right. There are 6 methyl groups directly connected to a double bond. We can count 1, 2, 3, 4, 5, 6. And what you can also see that there is a nice symmetry plane in the middle of this molecule. So this is an example how you can use oxidation reactions in order to elucidate the structure of an unknown compound. And why is this beta-carotene now important? It is important because it can be used in order to produce vitamin A. And well, that's it for today. And the exercises correlated to this lecture are the worked example 21.4 as well as the end of chapter questions, exercise 2 starting from D, as well as exercise 3 and 5. And in preparation for next lecture, please read already chapter 22.1, which can be found on page 1002 until 1013.